The first 3 weeks of the eruption here in Hawaii, crazy things would happen in the middle of the night. A new fissure would open up and it would threaten a new neighborhood. Thousands of people were evacuated from their homes. I started the Hawaii Tracker Facebook group to help people understand what's going on and get their questions answered.
Hey, how's it going? We're live. This is Fissure 20.
We had hundreds of people all throughout the neighborhoods sending in videos, articles, and images. We spend a lot of time making sure the accurate information gets out.
This is live. Still lava moving.
They weren't just sharing a story, they were helping their neighbor. If a family was being evacuated, the group would just jump in and help out. It was huge. They were watching out for each other.
Hello everybody, thank you for coming. Thank you for the support from everybody.
As we go through this, we're growing closer together as a community. When tragedies like this strike, you really realize how much you need each other.
We are the Hawaiian Volcano Education and Resilience Institute, HVERI for short. A lot of people know us from the 2018 eruption of Kīlauea in the Lower East Rift Zone. Working under Hawaii Tracker on the Facebook group. Since then, we've been trying to carry on and take the lessons, the hard lessons that were learned during that eruption and try and prepare for the next major disaster that comes to our island.
Yeah, so we do that through two different programs. One is volcano education, and the other part is digital resilience, which we address through online groups on social media. So the way the two programs work together is that the social media networks end up being a distribution pathway for all the information. And having that network in place means we can provide more than just volcano education, but any other preparedness information as well.
What we were working for really came about in the Mauna Loa eruption in 2022. Within hours of that eruption starting, we had the mayor, Mitch Roth, we had USGS-HVO Ken Hahn on the stream trying to help flush out a little bit of the ongoing because it's so new. It's completely different from our previous major eruption, which was 2018.
One of the things that Talmadge and I were talking about was how do we deal with social media? It was something we needed to figure out and get right. Our job is to get information to the public and make sure that the public get it as well as possible and as correctly as possible. When Philip and Dane started coming to and live streaming the meetings, it was great because we were reaching more people than we normally would. So when the eruption actually happened, we had this relationship. The interviews we did during the eruption, the most fun ones were the ones with Philip and Dave because they were more relaxed and we knew we were getting to the local community and people were asking questions. So those were the best, I think. I just want to really give a shout out to those guys and how we worked as a team on this eruption. It really worked out well and we got to a lot of people we wouldn't have normally gotten.
Aloha everyone, and welcome to our Hawaiian Volcano Tracker. Today is Thursday, January 22nd, 2026. Kīlauea is in another pause, awaiting episode 41. And how are you gentlemen doing today? Dane, how you doing?
Doing pretty good. Yeah, just waiting for the next episode at this point, and glad to be here.
Yeah, how about you, Lou?
Doing pretty good.
Next week.
Waiting as well. We know what the swarms have been happening. Wondering if my things are going to fall off my shelf or my teeth are going to rattle first for a while there. I think we're up to like the 5th swarm maybe that's happened of EQs. So interesting to see what's going to happen this time around.
Yeah, for sure. A little different than we've seen in the past pauses between episodes here. So yeah, anything you guys want to mention before we get into it here?
No, it's been chilly, just keeping warm in the mornings. But besides that, been nice.
I guess we should say that our schedule today is going to be largely dominated by a presentation from last week, Volcano Awareness Month, that was given at UHELO by Dr. Thomas Lee, seismologist. So we'll go through our own version of the update here in this first half hour, and then we'll cut to Dr. Lee and his hour-long presentation on seismology. All right.
That's it.
So that's it. Let's get some things moved around on the screen here. Get ourselves all set up. And all right. Aloha, everyone. This is our Hawaiian volcano summary for January 22nd, 2026. Earthquakes have increased under Kīlauea summit in the past 10 days since the end of episode 40. As the volcano continues to recharge towards episode 41. You're seeing a live stream here of the V1 camera showing continued degassing from both vents here at Kīlauea summit. But I can show you here from the V3 camera over the past week. We've had just a few breakouts following the end of episode 41 and continuing variable glow from both vents, which you can see in the last few days has gotten much stronger, including reports of occasional spatter from the north vent from the USGS. So you see that there, and you see here the ground tilt plot showing the recharge of the volcano since episode 40 caused a drop in pressure. We've seen a recharge here, slowed only in recent days here by ongoing earthquake swarms. And so if we zoom into this little section right over here for the past week, you see it here. We've had continued recharge. And these little deflation events are things we've seen in the past building up to our renewed episodes. But these, over the past week, correspond to small earthquake swarms occurring at the summit at the same time that seem to be taking away some of that pressure and delaying the onset of episode 41. So that's what you see on a ground tilt plot there. And here on the earthquake plot for the last week, you can see plotted by color at, corresponding to depth. In oranges at intermediate depths here under the summit, we see this big cluster of earthquakes, which has not been typical for this ongoing eruption now in its 13th month. We do still see south flank events and Ipahala events continuing. That's more normal. But focusing on a summit activity, you can see that our earthquake counts per week have jumped up here. And so we have our highest value for the past year of earthquakes per week, led by that swarm at the summit there. Here is an animation from the IRIS earthquake browser showing the occurrence of those earthquakes in several pulses or swarms since the end of episode 40, about 10 days ago. And the USGS has put out this map showing the location of those earthquakes broadly around the southeast part of the caldera with no obvious small cluster showing that building pressure underground. However, as it currently stands, the forecast for the onset of the next fountain is between January 23rd and 25th. So we're talking about tomorrow, Friday through Sunday, based on the current tilt models. That is considering that no changes of the deflation pattern occurs. And if we go down here to the analysis, we can say that despite all those changes, everything currently points to resumption of fountaining episodes rather than a change in event location for episode 41. So this is probably a longer term trend to track. We're expecting 41 in the next few days here. And just to remind you, everything is happening within the national park, within a summit caldera, and within the crater of Halema'uma'u, with no increased threat to people at this current time. And even with changes in event possible, the USGS is not tracking any changes outside of the summit region at present. So we expect, at least in the shorter term, all activity to remain away from people within the national park here. The biggest threat continues to be the VOG, which we see here from the VMAP VOG forecast dashboard. There have been variable winds over the past few days, bringing the low-level emissions from Kīlauea volcano to its typical southwest direction, but also north into the Hilo and Hamakua areas as well. So increased fog around the island with weaker winds, even between episodes here. And our current Purple Era Citizen Science Monitoring Network is showing those increased values across the island here. And that's our Hawaiian volcano summary for this week. All right, so let me get our hazard summary on a screen. That is our main concern nowadays. Everything else is pretty viewing and educational opportunity for us, all to help increase our mission of better preparing for the next disaster that does affect our communities. And so VOG is the issue right now and for most people. And so here's a camera on the side of Mauna Loa looking south towards Kīlauea, which is down in here in this area. And this is for the last 10 days or so, showing largely low-level trade winds at the start. This is just daytime views, followed by some variable winds. You see the plume blowing around a little bit more on the ground there, and as well as upper level winds changing as well here. Probably a little hard to see, so let's just zoom in already to the K2 camera. This is at the Uikahuna observation deck. There you can see the gases sometimes blowing at the camera, sometimes to the right. Normally trade winds will blow in this direction. Here we are mid-January in the midst of our winter wind pattern, which is still has a healthy amount of trade winds, but has a much larger proportion of variable and Kona winds blowing these gases into the observation areas in a national park too, as well as nearby communities. So this is a K2 camera. Last week we neglected to show that the K2 was actually the one that was pointing to this deck, showing which just suggested or they noted fallout of reticulite pieces up to 2 inches in this area. So I thought we could just throw in this video a little slower from the eruption last week at the K2 camera. So you can see here what that looked like with all the crowds of people coming in and parking around there. So let me replay it one more time, and let's zoom it in here to this bottom corner. So you can get this great view of the people coming to see this eruption at the national park. Pretty cool to see that after years of change up there. All right, so moving on, continuing to focus on our hazard and our gas. This is the V1 camera, just the daytime views for the last week or so. You can see a lot of whiteout in the camera view with the winds blowing in that direction, south towards the north, where the camera's looking south. And occasionally it blows off to the right as well. So good amount of VOG is the story here, the V2 camera, volcano house perspective. So you can see the plume blowing left, blowing right, going closer to the ground, higher into the sky. You can see variable is a good word for it there. And finally, the V3 camera, new V3PO. There it is. Same kind of change in the gas patterns, the left, right, up. And those are the daytime views, our gas views here. So looking at the VOG measurement and prediction program, which is out of UH Manoa, and looking at their VOG dashboard in particular, we come to this map when looking at our SO2 flavor of volcanic emissions here, the pure component that comes out. You can see it's drifting over the next couple of days here. A large amount to the north, but also to the southwest here too. It's kind of all around there. And if we now click to sulfate aerosols, which is as this VOG is affecting, is reacting with the sunlight in the atmosphere, and water vapor in the atmosphere as well, producing these particulates of sulfates, then you can see the impact is much broader, pretty much island-wide in the next couple of days here. So pretty striking view there. Probably should have included this SO2 layer in our summary there, but there you go, get the full version here. And looking at our interactive maps, starting off with the state here, everything is in the green according to them. They do show some increased readings, but still in the green. You can see a big gap in their data set right around a volcano, so that's not very helpful. That's why we like to go to Purple Air, which integrates all the citizen science network and the official government ones where they have them too. So for example, here we have some of the USGS stations in the national park. So in the yellow, but you can see it's reached into the orange red here earlier in the day. Yeah, yesterday. So one example of that. Let's close those. And let's try to zoom this back out there. So there, you can see that impact. This one north of the national park is one that's been catching a lot of the southern wind, and you can see there it's peaked into the red a couple of times and spent a lot of time on the yellow over the last couple of days here. So impacts are real out there with the VOG, even if they don't make the news happening every single day here. So our charts for the national park, or summary first, here is the map, and it's actually showing Namakani Payo campground in orange here. So catching that 15-minute average interval of still very unhealthy, very weak northeast wind. But when it comes to the charts, we can see the history of those a little more clearly. These are all in the green here at Uikahuna, our viewing deck we just showed you guys there. A couple of spikes of SO2 overnight and 10:30 this morning. At the campground, we just saw that. That's when I guess this is a little old here. Let me see if I can get this reloaded here to show you guys a little more current. Okay, still in orange, and our charts there. There's some missing data in there, but you can see there's the oranges as well. I don't know if how much that changed anything. Still, and the chain of craters road is notable. A couple of spikes of SO2. These are at 6:30 and 6:15 in the morning, so that you might have had some wind off the mountain coming down and bringing that VOG towards the end of the road. Normally, this site only gets readings from trade winds from the Pu'o'o area, so that's something that piqued my eyebrows, and I had to go look a little closer, and it looks like it was a north wind that actually brought up from the summit. And otherwise, that's business as usual, right? Gas coming and going. It doesn't seem to be in any one place for very long, but it does get intense while it is there. And that is the on the ground views, and we have a few satellite snapshots as well following episode 40. So here is the 15th, showing a southerly wind with impact to the north into Hilo for the VOG. The next snapshot, it flips with VOG to the south. The next one is southwest. Next day, still southwest. Now it's more north, and you can see this most recent frame here. It actually seems to be going further up in the atmosphere and dispersing all around, causing some weird pixelated readings there. So VOG is still the biggest impact, and as we expect 41 in the next few days, that's what to be aware of. Business as usual. If you need more advice, go to the VOG measurement, the VMAP page here. You can get links to all of these forecasts, resources, and all those kind of things. Preparing for VOG. Okay. Let's see here. I think I'm off a little bit. So let's go to some visuals now, visual observations. And we'll just look at the nighttime views of the V cameras here. It's a V1 at night. So you see some of these breakouts in those first few days following episode 40, increase of glow, and you can see it getting brighter here in the last 4 days or so, or 2 days or so, I should say. So that's the V1. The V2, a view that's more typical for tourists from Volcano House. You can see some breakouts in that little pit in the foreground there, some over on the west side or southwest side there. And there's both vents glowing, with the north one being more dominant earlier this morning. And the V3 overnight, there's some of those breakouts that we see here in the foreground following episode 40. Glow from the south vent and north vents. A little brighter with some spattering from the north vent. And that's our current activity there mostly. I can show you guys a couple other things. This is the B1 camera, daytime views only for the last week or so. And it's subtle, but there's a little movement happening in here. Now, it's hard to see exactly, but what you can most easily see is a dropping down. This is actually from the day after the episode until now. So the very first day afterwards, you see this degassing of the flow, and it's settling down there. But what's harder to pick up, I have to go frame by frame here, is that there's an actual rebound and uplift happening of the ground all right through here as well right afterwards. So let me do that here. Let me pull us back Let's see if I can do a frame by frame here. Let's find the right key point there, right? So there. From the day before to the day after, so earlier and later, there is that rising up you see right there. Very, very slight. It's not everywhere. It seems to be this band right in here, stuff on the middle right in here. So after or before, and if I come to the very beginning of the sequence, I'll show you the other part of it. At the very beginning, right there, the flow has first come through, and then it settles, then it degasses. So it comes through, it degasses, some time goes by, and then the next day it's bulging upwards right there. And that's really it for the rest of the animation. If I play it, you barely see anything other than that. It's a wiggle down, a quick bounce back up, and then steady the rest of the time. So interesting to note what was happening there, especially as we're noting earthquakes moving over into this area where this camera is and possibly making new pathways. The pathways under this crusted lava lake are still there and allowing injection of magma into these areas too. And if we look at the other point of view, the KW camera, similar kind of exercise, 1 image a day for the last week or so. Unfortunately, this big fog plume blows right in the way as we're trying to see what's happening over here in this far edge where we're just looking over there. So you can't really see much there. Otherwise, what you can see is this little bowl at the bottom of the lava shield in the pit here, that deflating as we've seen it happen every pause, just about over and over now, especially the recent ones. And similarly, if I come over here to the vent and the hill, you see this whole flow in here is also deflating with time, right? Really, it's really this whole ridge going down over there seems to be deflating. Those are the small, subtle changes we have happening observationally. USGS did also conduct an overflight. So here is their aerial image that they took as they surveyed the new layers of lava in the crater. And there is how they are doing their surveys by taking photographs, flying around it, and using photogrammetric processing. There's a mouthful right there. And collecting samples from the ground as well to do the chemistry, and do that for every single episode that they can. Take a look down into the vents themselves. You can see their configuration there. There's that kind of multiple complex north vent with several openings, right? But that's really the full release we have of images from the USGS overflight. And when we have this most recent thermal map taken of that day, where you see the inactive flows still hot, right? But noteworthy is over here on this right side, there's a couple brighter yellow spots. There are some little breakouts or ooze up flows or something happening there. I was not able to catch this in any other view, webcam, or anything quite so easily. We did see that this big pool of lava was overturning for a few days, so maybe it's just that, as opposed to like an actual ooze up injection from below. Can't really tell, but just to note that this was happening on the 16th, 4 days after the episode ended. That's interesting to see. So those are observations, and another quick look into the V1 camera here, live, the V2, and the V3 for our current views of what's happening there. So let's step over to our monitoring signals. We discussed, let's see, where am I here? How should we do this? Let me pull all the way down to about a week ago here, where we have last Friday. Note, if you remember last week, we had already seen the first earthquake swarms occurring following episode 40. And so they note here back last week, Friday, that sporadic earthquake activity continued, most recent occurring after 4 p.m. They noted that one at that time was what they called the fourth swarm broadly under the east side. And most of these have been less magnitude 2, most magnitude 1 or smaller, related to the pressure in the summit that we talked about. So from Friday, we come to Saturday. On Saturday, they note most recent swarm occurring that morning, Saturday morning. Small storms continue, one on the 16th. So there's 2 more of those, plus magnitude 2.2 earthquake. Let's jump up to Sunday. And how many seismic swarms there? 2 clusters Sunday. Coming to Monday, you see some more. So it really becomes how are they actually counting these as clusters or swarms or what are their definitions? Here's 2 more clusters reported on Monday. And basically every day they're noting more clusters there. 2 clusters again yesterday. This is on Tuesday. And coming to Wednesday, more clusters. And then today's article, in more detail, maybe is the most relevant, the most current thing here, right? Elevated micro-seismicity continues in the summit region. 2 multi-hour periods of elevated micro-seismicity occurred over the past day. The first yesterday evening and the next this morning. Neither period saw earthquake activity as strong as swarms earlier this week, and only 4 earthquakes were large enough to be located over the past 24 hours, right? So this is noteworthy. They refer to these micro-seismic swarms, and they can tell earthquakes are occurring there within range of these stations, but they couldn't tell you exactly where, and only that they're nearby enough to be picked up by that station and not ones further away, right? And normally you have to have an earthquake be big enough to register on at least 3, minimal 3, but ideally more stations to then triangulate where it's coming from. And if it's too small to only appears on 1 or 2, then you can't do that triangulation. That's basically what we're talking about, them being so small there. So that's what's happening there. Lots of those earthquakes, the tilts come almost all the way back to what we lost. They've measured SO2 most recently on the 14th at 1,550 tons per day within that range, typical range there. So overall, the earthquakes are related to migrating magmatic pressure within a summit region. The impact on our next episode of fountaining is unknown at this time. But as we said earlier, everything currently points to resumption of fountaining rather than a change in location. Right? All because of the repressurization, the glow, appearance of event, all that coming together. And if I might, let me just jump ahead to the signal we have. Where is it here? This one right here, right? And what we're looking at, Cliff Notes version, is that amount of tilt drop, or that amount, corresponding to how much work all these micro earthquake swarms are doing. So it's doing some work, clearly enough to affect the tilt meter there and there and there, right? But look at the scale of what that's doing compared to the scale of the repressurization of the actual reservoir. So this is a much bigger value, much bigger magnitude event happening than these little things. And so right now, this is minor compared to this. That's the kind of the short version of what we have going on here. Right? That's what they're saying here. We're seeing that there's changes in the pressure happening, but all signs still show likely fountain from events that we already have for episode 41. So that's some of the monitoring data there. So what else can we show you guys here on these tilt plots or these weekly plots? Here's earthquakes depth versus time. So there's our shallow pulses of earthquakes. They're there coming through. You see it's kind of quiet under Pahala, and then Pahala activates. It just happens to be how it manifests. They're completely unrelated as far as we can tell, or even AI can tell this far. And continuing, there is the distribution, which we talked about earlier. Let's see here for the last month, how these pulses look. A little bit heavier in the last week and a half or so right there. Although they were occurring beforehand around the volcano and just not so clustered under the summit. And so there you see our current little wiggle we just examined. So it does bring it into question. We've been seeing these little delays for many of these episodes prior to the actual onset. And even if we haven't seen the earthquakes, has there been this same magma migration pattern movement to delay things? maybe into areas that didn't require as much braking, but just a little bit more squeezing, right? And now we've gotten enough of those in, we've kind of run out of that space, and now we're having to either crack more space for the magma directly, or that whole building bulge below is causing cracking, maybe not right next to the magma, but in areas around there that all have to shift to accommodate the magma bulging from where it is, if that makes sense. It's hard to describe those things, those three-dimensional things there. So overall, there's our summit tilt pattern. We're expecting it to return, and we're just seeing these little changes here and wondering what that might mean. As we all wonder, how much longer could this summit eruption go? And just as likely as we've seen some change happening of the event, we could be sitting here a year from now talking about, isn't it incredible it's still going in the same place after another year? And look at how full the whole crater is. Right? That's the whole range of possibilities that we have here. So for the last year of earthquakes per week, you can see that spike here. Our current week is going to come in pretty high too. Our GPS is showing that same extension north and south across the crater. See a little bit, we're almost at the same threshold as before. You can see that's going to a little bit increasing over time. So maybe not quite, almost there. And that's our main signals that we have here. So we'll skip the 5-year things here since we're running a little short on time. And I do want to talk a little bit more about the earthquakes. And so let's put up the earthquakes banner here and just recap this info statement from last week, the 14th. After the third swarm of earthquakes, they put out this statement noting that most of the earthquakes are volcanotectonic earthquakes that accompany crack opening due to magmatic pressure. Elevated seismic activity of recent intensities have not been seen at the summit since the start of the eruption in December 2024. The small swarm did precede a new fissure opening in a wall of the Kīlauea crater just south of the vents at the start of episode 30. It's yet to be determined if these swarms after 40 will have an impact on fountain activity at the surface. Volcanic systems remain a complex balance of magmatic pressure and strength of the surrounding rocks. If the rocks weaken, one possible outcome is injection of magma into a fracture, creating a dike. If the magma breaches the surface, a new vent might be created, shifting the focus of the eruption. Historically, episodic fountain eruptions can cease when the magma supply is diverted in this manner. So that's why we're paying so much attention. Currently, all activity remains beneath Kīlauea caldera, and there's no observable evidence that magma is migrating away from the summit area. Both the east and southwest rift zones remain quiet at this time. So that's the key info there. This is really the money statement from last week. To look in a little more detail, here's that IRIS earthquake browser animation once again. Yeah, so we're looping. Here we are. Yeah. So you see they're out broadly here in the southeast part of the summit. Clustering near. This is Kīlauea crater right over here. So that overlook, people are looking at the fountains from right around here, looking this direction, is right over that area, right in there. But they come in these little pulses, but you see they're not very concentrated. It doesn't look like an injection of a dike yet. It just looks like the growing pressure of the reservoir cracking all around in a broad area all around. So here's a map a different way.
Hey, Phil, can I jump in here real quick? I got a question for you. Since everybody's been talking about the last week or so on with the swarms happening and a possible new location, USGS just kind of confirmed there that it's most likely going to come out of the vent where all those earthquakes are swarming at Kīlauea. That's kind of in the general direction of the fissure that came out in one of the past episodes. Does that have anything to do with the direction or location? Is there anything connected there?
It's really hard to think about these things in 3D. What you have to remember is that these earthquakes are occurring at a certain depth, right? So they might actually be closer to the magma chamber than they are to the surface. And it's relate more to what's happening there in the magma chamber than they are to some crack when it's about to come out, if that makes sense.
Mm-hmm.
Excuse me.
I know we always try to put things into some type of three-dimensional visualization to try to make it make sense when the elevations don't really line up or the coordinates don't really line up. But sometimes looking at it makes your mind kind of twist your mind a little bit. And I see the comments in the videos. Sometimes I see it in the chat.
That's a interesting question. Always comes up with why that fissure came up that wall, and does that have anything to do with possible future of eruptions happening?
Well, it came up the wall because the wall was a crack that was already there, and fissures like cracks that are already there, and that means they like walls. They like crater walls. Always, that's kind of always the case. Lots of examples of that. So that's more about like the surface as that pressure is coming towards the surface, however it's coming, and it feels like how the surface is responding to that. It actually will move in a direction to align with that shape and come out that way through the crack that's already there. It's hard to describe that. So when the other thing that's important to remember is we have this shallow pit of lava with a crust over it. We have a shallow Halley magma chamber somewhere underneath here. It's thought to be more or less in that area right in here as well. Then below that, or below and slightly off to the side, we have the deep south caldera chamber, whose center is thought to be right here also. So there's a lot of stuff happening all in this area at depth, right? And so to say, okay, just because they're all stacked on each other, it's harder to untangle those in 3D, you know, right? Like there might be more spacing vertically between them than there is on a map side to side, right? So like that crack where that lava came out of here is not as close to the deep chamber as it is to the shallow chamber, as to the et cetera, but all the things are all stacked in the same vertical slice of ground drawn through here. So it gets really messy. So I never give you a real answer because I don't have a real answer, you know, like it's all discussion always, right? We don't have the answers. It's more about thinking and talking through what the variables are and what contributes, what the range of possibilities may be. So
That's
we don't
good.
really know, but
all these answers just bring on more questions. It's perfect.
To me, when I see it this broad and spread out, it almost is showing something deeper, right? That's like showing it's cracking at depth. And it's being felt over a broad area. It's not, if it comes to the surface, it's going to focus into a small area and cluster in time and space, and that's going to be your fissure.
That's actually one of the, you know, when Ken Hahn said that this eruption, the rate at which it's the magma supply is more than the supply rate from depth. Okay, well, it's coming from somewhere, and the biggest somewhere is the South Caldera. And my question then was like, so what, is it free? Because there's no earthquakes, it's just withdrawing and no adjustments. You know, it was always, so seeing this, I'm like, is that just the South Caldera adjusting to all of this supply that it's been getting pulled from? Like I don't know.
That's possible as well. Yeah, I mean, what we're not getting with all these earthquakes is like each earthquake. I mean, it has to be big enough to do enough math on it, but they actually can tell, like, is that earthquake from the rock pulling apart from cracking under tension, or is it getting compressed and pushed together and getting, you know, there's all kinds of things you could pull out of there. So maybe there's more that we're not seeing from these signals, as far as giving them this clue that it's actually magmatic pressure migrating. Although that doesn't exclude the pressure migrating, meaning there's less pressure going to be there at the summit.
Right. Interesting.
So it could be that, and either way, it could be a sign of something changing. Whether it's like, well, are we running out? Is there some kind of, why is it doing this now and hasn't done it before? That's really the question, right? Is it either more, is it pressurized where it's having to move? Is the dynamics of where the pressure is happy to be, is that changing? Is it losing enough pressure to start reacting, as you're saying, Dane? I mean, I think those are all great questions, and really only one way to find out is to keep, you know, waiting for the next episode next week. What Kīlauea does, right, day to day. It's the series that never ends here for us. And it doesn't take any Hollywood production for her to do her thing here. She just goes. So yeah, that's really the story. Is the many earthquakes there. There's another view into it. We have the earthquake map for the whole island here, and really that cluster is this red right in here. Everything else is pretty normal, although there are some bigger events. Magnitude 3. On Mauna Loa's southeast flank here towards the south, worth noting. There is a magnitude 3.5 over here on Mauna Loa's western flank as well. Everything else might be deeper adjustments, deep Pahala earthquakes, south flank, things that we're more used to seeing. But if I can zoom it in to the summit region here, you can see another take on this cluster of earthquakes right there. And we got a different view here, looking at the size of the earthquakes. So the largest in the last week was about 3.5 on the Mauna Loa west flank, then a 3.2 on the southeast flank. Both of those fairly shallow. Then a deep Pahala event at 3.2, and everything else under magnitude 2.5. So I want to zoom into the summit region here, and within this area now, our largest events at 2.2 over there, very near the surface. Another 2.2 just to the southwest, and occurring 1 second apart, those two. Something broke at that moment. Magnitude 2 up here, maybe not as related, hard to tell. That one's a little bit off of the main cluster there, and then 1.9s and smaller continuing from there. So those are the earthquakes on a map there. It is, we can put up the volcano watch, which was released just a few hours ago here, or maybe an hour ago. What do small earthquakes beneath the summit mean for the ongoing eruption? So here's where they released this map. They note that the occurrence of all those tiny earthquakes. Up to 25 earthquakes were detected during one of the swarms, but the actual number of earthquakes was more because many are too small to be located precisely. The only other time earthquakes occurred like this was when a small intrusion formed in the southwest wall before episode 30. So a lot of the same information in here, just kind of putting it back together. These swarms may be our first signs of changes in the ongoing eruption. It was not yet clear exactly what that change will look like. They're widely dispersed, do not delineate a specific pathway. Information patterns during the swarms show that a small amount of magma was possibly being transferred from the high magma chamber, likely in the surrounding cracks. So there's our biggest answer as to what's actually happening, and as well as looking at the tilt drops, right? Like seeing the pressure high and then an earthquake swarm occurs, it drops, suggesting the magma is going somewhere else, right? Rather than it actually being a contractional event there. And let's see there. And during that previous episode 30, the earthquakes were all clustered much more tightly toward the surface, so suggesting a well-defined crack there. So all that's because you're looking for clues of how the eruption could potentially change. That's why we're looking back at Mauna Ulu and Kīlauea Iki and Pu'o'o and all those other fountaining events that we have for reference. But really the long and short is that we haven't ever seen anything quite like this on Kīlauea Summit. Even in geologic record, it's hard to untangle something quite like this happening. So we'll have to just wait and see what actually occurs there, right? And that's really the story of the earthquakes and awaiting episode 41 here. Before we come into our break, I just want to touch base on Mauna Loa very, very briefly, because we have opened this can of worms here this year. Our status is unchanged at normal and green here from our monthly update. And our signals are showing occasional small deep earthquakes still occurring over the past week. You see here, there's 3. We look over the last month, and you add those 3 to the previous week, and you can see it looks like almost like they're shallowing there, but it's a very slow, drawn out process. Now we come to the last year, and you can see it certainly look more like a cluster occurring there. Like it might be some movement from depth of magma. Then you get to the 5-year plot, and it starts looking like a actual event, similar to some of these previous ones that we see as well too. So I just point this out because we're watching it happen in slow motion. We're in the middle of it right now. It's like not one big pulse. We can see it tracking through like over a course of a day. It's just like a little bit here, a little bit there, a little bit here over the course of days and weeks and months. And just over this moment in time, we can see that a little bit of that activation of the deep source there under Mauna Loa Summit, the most interesting thing. Overall, it's a very small increase in actual numbers compared to what we saw building up the 2022 eruption. So we'll just keep it that brief here at Mauna Loa today with just one final view of the summit caldera, Mokua Ve'oveo, as it looked earlier today. So, all right, I'll pause there and pass it to you, Lou, for
a lot. Oh, there's a lot going on. We're all over the place today. Dane and I are. Hey, Dane, let's start off with since Phil's got us up there on Mauna Loa. Let's start off with what's going on this weekend, shall we?
Yep. Got a little prep fair happening. You're on Saturday. What does that start at 2?
2 o'clock.
At 2 o'clock at the Ocean View Community Center, and we're going to have USGS, Civil Defense, National Park Service, we're going to be there. The Ocean View Resilience Hub folks, as well as KWXX with their new radio station extension down there, allowing emergency broadcasts to be able to reach the Kau region. So come check it out and get everybody the information they need there. Try and answer some questions. If you have anything, this is a place to come to get ready for the next, not only Mauna Loa, but also the tropical storms, fires, whatever else, that we are exposed to out here in South Kona or in south of Hawaii Island.
Yeah, I just went ahead and dropped the link in the chat. So if you are in the Kau Ocean View area, you want to jump into that. It's a few questions, gives you an opportunity to ask the local emergency managers, the others that will be there, questions so we can get it to them and they can answer those directly. You also get a chance to walk around and talk with everybody. It's a little bit different than what civil defense and their preparedness fairs have been in the past. It's a micro event. It's going to be more interactive instead of just speeches, I guess, put it another way. There's going to be prizes. We got buckets of stuff, I think, there as well, Dane. And remind me, the KWXX, it's out of Discovery Harbor. Is that where the new radio station is out of? Do you remember hearing?
I don't know where.
I don't either, but I think it was. So that's a big deal for Kau because the whole area down there, they did not have any type of reliable information over the airways. So that's good to see. So come by, check us out. Dane and Phil be taking pictures with everybody and signing autographs. So come on by. We also will be live streaming. We'll drop that link out to everybody in case you can't make it. If you are maybe on the mainland or somewhere else around the world, you'll be able to check it out online and see how we're doing things in disaster preparedness over here on Hawaii Island.
Yep.
All right. Anything else you want to throw out there, Dane?
Nope. Just we'll have the VODs up if you miss it as well.
Yep. There we go. All right. Let's move into, we're doing a modified community corner this week because everything is focused around Volcano Awareness Month. And let's go ahead and drop this up there. Maybe. There we go. And here is the event that we were just talking about here, Saturday the 24th, Civil Defense Disaster Preparedness Fair, 2:30 to 5 p.m. with presentations at 3 o'clock. There's other stuff happening around the island. You can make it a whole day of it, of different things going on. Remembering Halape and Onizuka Day is also going on. Next week, there is a year of lava fountains that's going on. Matt Patrick on Monday is going to do that talk at KMC in the Ohia room. On the 27th, down at the Vault of Volcano House. This one, I'm not sure you're going to be able to have the opportunity to view. We are not live streaming. It is only limited to 20 participants, and it's by ticket only. So that's a tough one for us right there. Year of lava fountains again on the 28th. This time it's by Deputy Scientist in Charge David Phillips. That's going on at the Ilioma Imiloa Astronomy Center at 5:30. And if you can squeeze us both in, we'll be live next Thursday, the 29th, and you can watch Dr. Liz Gallant from Hilo at 6 p.m., the Volcano Arts Center, giving a talk on Volcanology 101. So that is pretty much what's going on in the community for next week. That should keep your hands full right there. You can find all this. I'll drop this link in the chat as well so that you have this schedule because there's a lot going on there. So give me a minute and I'll put that in there. All right, Dane.
Yeah. As far as our coverage, right? We're focusing on next week's talk by Liz, yeah. And so seems like chances are we'll have episode 41 by then. And so maybe the following week we'll have a recording of Liz to share with you guys, similar to what we're doing today with Dr. Thomas Lee.
Yep, great. This is the one we're going to capture next week, right there.
It's nice because we can do those with they do some evergreen talks, so to speak, or things that stay relevant longer than an update about the current conditions. So that's why these type of talks where you can sit on them for a little bit and show them at a more opportune time, as opposed to crowding in around an episode.
Yeah, and that's what everybody's going to find from the video that we're about to share that we have picked up from last week that we recorded. So it's one that you're going to want to watch over again, and we'll be able to share parts of this at any time. It's a good one. So let's keep moving, Dane. I'm going to go into observations for the week real quick here. I have a couple. It kind of follows up with what Phil was going on before we hit the mid-roll. Observation. Music's a little loud. Music by Dane DuPont. So that has been happening from this morning. We're starting to get spatter. There's actually spatter coming out of the North Vent right now. There's a little trio of sails in the spectro, so that we just had another little earthquake. A couple earthquakes hit. Episode 41 is definitely ramping up.
Yeah, I mean, gonna have to keep eyes on it tonight, probably through the next couple of days until it goes, and we'll probably get a bunch of the prequel activity. Don't know if it'll be north-south vent, but or both. Alternating, at this point, it really haven't gotten the flows yet.
No. But here's Phil has been talking about the swarms. That's been on everybody's mind. So I picked up and recorded what it looks like. This is regular speed of one of the swarms that have been coming in, and then kicked up to 8 times speed. And you can see just how many come in at a time. It's one after another, nonstop.
Yep, definitely noticeable difference. So yeah, we'll see where this gets us, and it looks like we're getting towards that forecast window. So should be
window is supposedly open tomorrow. Tomorrow's the possible open. Yeah, possible open.
Yeah, that was today.
But things change. Things change overnight.
Yeah, these things can sneak up on you rather quickly. But we've seen the last few ones more go towards the delayed aspect. Yeah, delayed until. Clip that.
Almost over on this one. I'm going to get one more piece in here. Let's skip it a little bit. I guess I was enjoying the moment when I was putting this together with the music.
I guess so.
Sometimes you get into the music and just kind of like, oh, how long am I doing?
You're just watching those spectros for like 5 minutes. I know.
Here's the tilt. I put it on a run for so you can actually see. There's the drop and tilt before or as episode 40 started up, and then it'll show the swarms that happen with the tilt dropping in through here. These big old potholes that we keep seeing.
Yep. Pattern repeating, that jagged sawtooth. And then it has a little bit of that last episode was kind of a dull sawtooth blade.
Right.
Get a rock with that one.
Zoomed in so you can kind of see what it looks like there. And there is our observations. I've got one more for us. This is from Janice Way. She is a volunteer up at the park, a photographer and excellent videographer as well. And she let me use this. This is the night that the Tephra was raining down on everybody during episode 40.
Hard to even see.
Pretty mild on that one, right? Imagine if it's actually blowing at you, like how much bigger and hotter and everything falls, right? These guys are kind of just out on the edge of it, laughing, no big deal.
Yep, the wind not pushing right at them at least.
You can see some of the chunks right there through the screen.
Yeah. It's an experience at least, you know that.
Yeah.
It's
definitely.
Catch it with your
catch
mouth
it on your tongue. Yeah, don't do that. Much as geologists are famous for licking rocks and eating rocks, I would not recommend this one.
No. So there we go. Thank you, Janice, for letting us use that tonight. Appreciate that. And Dane, I'm going to let you walk us through our mid-roll here with some thank yous.
I did it. All right. Well, thanks everybody for tuning in today. We rely on the viewers like you to come through and help to keep this relevant, right? Like subscriptions, the shares, all that stuff really does help. I know I say it all the time, but it does. We also like to thank, we had some donation come through today, but like to thank County of Hawaii through the Bye grant that has helped support this program as well as our other programs. And looking into 2026, we might be throwing Kīlauea recovery back into the mix. I'm thanking them as well. So appreciate all the support there. We did have some donations come through. We had I think I got them here. We had a $50 donation from Ed. Appreciate the support there. $50 from Mark. Thank you, Mark, over longtime supporters, and one other supporter, Norm, with a $20 donation. Norm from Hawaii. All right. And I think that gets us through. We did have a couple questions here for you, Phil, if you want to, or a few questions, if you want to do those before we get into it.
Yeah, let's give it a shot.
All right. Hugh asks, another question, is the weight of all that lava piled up on top of itself beginning to compress?
I'm not sure. Like the lava itself, probably not. And that rock, even with lots of bubbles of gas, I mean, normally the lava's got to be still fluid in some ways for it to like degas and kind of subside, deflate, so to speak, right? And then once it actually hardens, I mean, you find it millions of years later with a bubble still intact in a rock.
I think I would assume it's more about that tephra hill and stuff like that, because that we do know compresses, right? Think of Fissure 8 when it was at 220, and then we check it back and it's like 180. It's just compressing itself down because it's just so fluffy at the top.
Yeah, I mean, there's a couple of things that they mentioned. They mentioned that the tephra hill itself, like if the stuff falls still hot, then the stuff on the surface is cooling off, but the stuff on the inside stays hot for a while, and in fact can be liquid still for a long time. And then that's where you can still see it compressing and mobilizing, right? Still by losing gas, right? By allowing the liquid to kind of coalesce and the gas to escape. And that's why we've seen, on the side of that hill underneath on the cone, we've seen flows of like red material for like over 10 days after the flows actually stopped, right? It shows how hot the inside of that thing actually is. I think there's some of that definitely happens as well. Yeah, for sure.
All right. Next, we have Mark, who asks, do we have recent inframetry data that should shed light on the seismic activity? I'm not sure if they asked that, when they asked that.
Yeah, so I mean, there is a new insert that came out that I didn't bother showing today. It's all captures as the big deflation signal, episode 40, right? And likewise, inflation of 41. Like the signals we're seeing of the earthquakes are so small compared to the actual inflation deflation of the magma reservoir that it barely shows up. You'd have to have an image that snapshots without an episode occurring, and only that, and no inflation or deflation otherwise happening. So the answer is no, unfortunately, right? The size of the signal is so small.
Makes sense. That overlapping area thing all over again.
Right.
All right. Paul asks, episode 40 on the ground tilt did not go down as much as previous eruptions, but 40 went for 9 hours, about the same as previous eruptions. What's your thoughts on that?
Yeah, I mean, the duration has varied quite a lot also, right? There's a range for sure. What we were seeing before was when both north and south vents went together at the same time, then it was lasting half as long. It was lasting 5 or 6 hours, right? And the tilt was going down twice as far as well. So this is almost like a throwback to the old version, right? Where only one vent goes off at a time. And it erupts for twice as long and puts out half as much lava, actually. This one put out 5.5 million cubic meters, which is a lot, but it wasn't the 9.3 that we got the last episode, right? It's, 40% less. That's a huge amount less. Yeah.
All right. Well, that gets us through the questions that I got. There is... Oh, no, we'll do it for the questions. Yeah, and we can get into our second bit here, which is going to be our presentation at UHS by Professor Thomas Lee.
All right, sounds good. Lou, you want to do any intro to this, or should we just?
Yeah, I can do a little quick intro since I was there and got to watch this already. This is Professor Thomas Lee, as Dane just said, from the University of Hawaii at Hilo, and hold us there. Thank you. And he's going to be talking about not just how or why the ground shakes. He also goes into the history of measuring the ground shaking, hundreds, if not thousands of years of history of recording and how they measured earthquakes. Probably one of the best speakers I've heard in a long time. Very knowledgeable and breaks down the history of kind of the Kīlauea as well as other parts of the world during his presentation. So I don't want to spoil anything. There's a lot in there that he says. So sit back, enjoy this, and let's roll the tape.
All right, sounds good. So yeah, it's about an hour long, and we'll very briefly at the back end come on and give some quick thoughts and hop off, since we'll be going about 2 hours by that point in time. So thanks, Lou, for the intro, and yeah, here is Dr. Thomas Lee.
Thanks very much, Steve, for that nice intro. So today, the title, What's Shaking at the Volcano? As kind of indicated by the parentheses, sort of has two parts to it. There's what's shaking and at the volcano. So what I'd sort of like to do is divide up this talk into a first part where we really actually take apart and ask, well, how do you actually measure shaking? What is actually going on when we record ground motion? And then the next part, which is when we record it, why is that helpful for understanding something like a volcanic system? So the actual field that I would technically say I am within is something called seismology. And what seismology is, if we break it apart, is seismos, shaking, and logos, or reasoning, right? In other words, it's just the study of why things shake. And that involves both earthquakes themselves, so the actual events that are perhaps rupturing the ground and releasing energy, the source of shaking, if you will. And then also what we can tell by looking at that shaking as it propagates through the earth. Just like when you go to the doctor and you get an x-ray, they send x-ray waves through you, and from looking at how those x-ray waves reach some receiver, they can tell if your bone is in the right place. Just like that, we can look at some vibrations from an earthquake going through the earth, and it tells us something about the structure within. This actual earthquake here is a pretty interesting one from 1995 because it was a very, very deep earthquake. This occurred at about 600 kilometers depth, somewhere below the Marianas Trench. And then those waves went on through the earth all the way to Massachusetts. So this is recorded on the other side of the earth. And as it went through, it picked up different things. You'll see it's not just one big shake, but a whole bunch of packets, if you will, of waves that arrive at different times. And that is kind of interesting because that tells us a lot about what's going on inside of the earth. If we have a bunch of stations, we could maybe get a little clearer idea of this. So what you can imagine is that we have time on this axis. And what these are in these funny looking letters are seismic stations at different distances away. So on this axis, we have distance going up. In other words, after an earthquake starts, after some time, the waves are going to start traveling further and further away. And people have gone in and they've said, okay, here's one packet. There's a certain packet which we can distinguish that arrives first. We call those P waves. And they have a straight line. In other words, they're moving at the same speed. Those are red. And there are these guys. Those are also moving at the same speed, but a little bit slower. Those would be S waves. Keep in mind that they basically make a straight line because they're going the same speed and they're traveling through the same stuff. Now, if we look at the whole record, now we have a lot of distance. So like opposite side of the earth here. This would be very close to the source down here. if we try and follow those lines, you'll see that up here they do something kind of funny. They don't travel in a nice straight path anymore. As you get further away, they take a little bit of a jog, as if they sped up or slowed down or did something different. And in this region here, it turns out that just like only certain X-rays are going to sample certain parts of your arm, and if an X-ray goes through here, it's not going to get your elbow. It has to go through your elbow. Only certain seismic waves go through certain parts of the Earth. The ones up here that look a little funny, they went through the core. And because the core has a certain material in it that travels really, really quickly, or allows seismic waves to travel through it really, really quickly, we see a difference in the waves. In other words, we've actually never gone any deeper as humans than about 10 kilometers below the surface. But with seismology, we can look thousands of kilometers down into the Earth and see what's in there. 1,000 kilometers is probably overkill if you want to look at volcanoes, but it's still deeper than we can dig to look at what the magma chamber looks like and those sorts of things. So what I want to kind of next talk about is, well, I've been kind of going on and on about seismic waves, seismic waves. What are they actually? The thing is that they're basically just an up and down motion of the ground, just like a compression and decompression of the air would make a sound wave. Waves are the reason you guys can all hear me now, and they're how a lot of different things travel. We could look at an example here of some waves. Now this looks pretty complicated. There's some sudden motion and then it kind of decays away, and another pulse and it kind of decays away. And then there are a couple more of those. It actually has a pretty nice structure if we zoom way in on it. And as it turns out, this is an eruption, but maybe not exactly the kind you might be thinking about within this context. This was a 1978 eruption in California, specifically at Sunset Sound Recorders in Hollywood. This is Van Halen's eruption. And the idea is that, at the end of the day, these wiggles really don't look any different than the rest of the ones I'm going to show tonight. It's not anything really exotic. It's just shaking. It's whether the ground shakes and we feel an earthquake, or whether the air particles shake and you hear me, it's a wave. And so this analogy, I think, is something we could pull on a little more. It's a nice kind of simple way, in some ways a little more intuitive way to approach thinking about seismology, which is that seismology, at the end of the day, is listening to the Earth. Now, Earth vibrations generally happen at such a low frequency that as humans, we're not going to hear them. However, we could speed them up, and then we can use, rather than just our feeling senses when we feel an earthquake, we can use our hearing senses to think about what we might be listening to. This is called sonification. And in this example, someone took the 2011 Tohoku earthquake that happened in Japan, and they just sped up the record, essentially, so that you can hear it. So rather than looking at just the seismograms of the earthquake, we could listen to it, and it sounds something like this. So that would be the main shock. That's the big earthquake. And all these little booms afterwards are aftershocks. It's not unlike the sound of rolling thunder when you hear the sound waves coming to you through the air. It's just that this is traveling through the Earth. You had a big release of energy. Could be on the other side of the Earth. I mean, I believe this is recorded in Australia somewhere. And it's not actually very near the source, but we hear it even far away. Now, this kind of brings about an interesting question. How do we hear? How do we hear that, or me talking to you, or Van Halen's eruption earlier? Well, as I speak, I'm vibrating air molecules. Those travel to you, and then they vibrate your eardrum, right? That allows you to be able to perceive that sound. Now, if we want to do the same thing with the ground, we're doing our seismic waves now, where instead of air particles shaking, everything's shaking. The ground and everything that's on the ground is shaking. And this poses something of a problem. This nice stick here. I could do that, and try and see if the ground is going to shake. But the problem is, I don't have a frame of reference. Because if I take that ruler and put it on the ground, it's going to shake with the ground. Everything's going to shake. It's really not a very good way to try and understand how much something has moved when everything moves. If everything moves, nothing moves, right? So that's out. But there must be another way, because clearly we feel an earthquake. We know stuff moves. And the way that we are able to come out and feel that is because we have momentum, right? This was something that you can kind of get an idea for. If we take something like this chair, we have this stick. It's not going to balance nicely by itself. But if I move the chair, it's going to move to one side or the other, because the top of the stick wants to stay in place, and the bottom is being moved by the earth. It's a sort of inverted pendulum, and someone that was pretty smart in China, more than 1,000 years ago, came up with a similar idea. This guy, Chang Heng, lived in about the 1st century and 2nd century. He was a geographer and an astronomer, and he came up basically with this idea of a stick sitting upright. And if the ground moved, momentum would keep the top of the stick in place, and the bottom would move. The idea being then, he could detect earthquakes. Now, if he wasn't there to watch the stick, he needed some way to tell if it had moved, and the way he did that was quite clever. Here's his stick, and there are these very, very delicate little latch mechanisms, essentially, all around it that hold a little bronze ball in the mouth of a dragon. It's a great scientific instrument. The seismometers I use now don't have little brass dragons on them, which is a real shame. But this one kind of did. And so the idea is that when the earthquake happened, in this case, the stick is moving, but really you need to imagine the top of the stick staying still and our whole room moving in an earthquake. When that stick moves, it will open the dragon's mouth, and the little ball will fall down into the mouth of a frog waiting below. In this way, he was actually able to not only detect the seismic events, but actually tell someone, well, that event happened, and it happened in that direction, and came from over there, from the east or from the south, because that's the frog that the ball dropped into the mouth of. This was actually an instrument that worked fairly decently as long as the earthquake was big enough, and it was in use for hundreds of years in China. It was sensitive enough, apparently, that you wouldn't feel the shaking, but this would detect that there had been an earthquake. So he was something of a wizard of the time. He had his magical vase and his frogs, and a ball would drop into the mouth of the frog, and he'd go, in about a week, a man is going to come on horse from the south and tell us there was a big earthquake, and it was catastrophic. And it turned out to be right more than a couple times. The technology is actually one we still kind of use today. There's something called a seismoscope in modern sort of seismology. And what it does is it will measure horizontal motion by taking some smoked glass right up here and having a big weight. So that weight is generally going to want to stay in place. And as the shaking occurs, it's going to scratch with a stylus on the smoked glass so that you end up with something like this. You basically are going to have that stylus sticking straight up, moving around and shaking in the earthquake, and it's going to leave you a record of the way things moved when the earthquake happened. Now, these are all what we would call seismoscopes, because if I showed you this glass plate and I asked you, was there an earthquake? You could tell me, yes, there was an earthquake. But if I told you, well, how did the shaking start and how did it end? You'd probably go, I'm not exactly sure, because I don't know if the line starts down here, there, or if it kind of did this back and forth bit first, or if it did the round and round bit first. It's not quite clear just from looking at that glass plate. So we get the motion, but not necessarily the timing. That's why we would call this a seismoscope as opposed to a seismograph. A seismograph allows you to understand the timing of something. And it works very much on the same principle of inertia as all these other things. I've been talking about inertia and momentum, and we should give it its proper name and give Isaac Newton some due. This is Newton's first law. And all it says, if you're not, need a little jog to your memory, is that objects at rest tend to stay at rest, and objects in motion tend to stay in motion. So what you have to imagine is that we just have a ball that's magically floating above the ground, right? Now, we don't have magic, so what we do generally is we have a little armature and we have a spring, and that's going to hold that mass up. The beauty of that is that when the ground moves, because that mass wants to stay in place, the spring extends, and even though everything in the frame of reference, the armature, the top of the spring, and the ground are moving, the ball more or less stays in the same place. Same thing. When it comes back down, so long as it comes back down quickly enough, this guy's still staying in the same place. Everything else has moved down. So this sort of shaking, where the ball stays in the same place and everything moves, now actually allows us to do something kind of interesting. Now we stick a ruler on that armature. So now we can measure the motion. Because the ruler is going to move, we know this to be true, but we can measure the ball's position on the ruler, and because the ball is staying still, when things move, like that, we can see that we actually are measuring the change in the motion of the ground because we have this ball, which due to inertia is staying still, and then allowing us to measure how much everything else is moving around it. Okay, so that's some shaking. As far as time goes, the way that that component would go in is, again, we have a spring and a mass, the frame fixed to the earth, just like we showed earlier, is with a recording device. So if people had been up to Jagger before and you remember seeing those big drums of paper with a needle scratching on them, the needle was actually connected to a mass on a spring somewhere. And what it was going to allow you to do is this. This is a simplified thing, but just stick a pencil on the mass, essentially. So now when the earthquake waves come, everything, paper, frame, spring move, but the mass stays the same place. And as a result, on the paper, you're going to get a direct measurement and a direct drawing of how the earth shook. There's another component here as well, which is that if you look at the paper, it's moving, right? Those drums, like the ones at Jagger, they slowly rotated. And because of that rotation, that pen is actually drawing a line. And so you can see the timing. We can see that this little shaking happened before the big one. And these seismograms that come off are basically just taking that drum and unwrapping it. And when we unwrap it, we end up with a nice record of the shaking, right? This one is actually from Massachusetts, but the idea is that this was once wrapped around a big cylindrical drum, and that pen attached to the mass drew a big spiral coming all the way down the record. And so you just read it like a book. You start at the top and you go left to right, top to bottom, down through each line. Now, there literally are some seismic instruments, some seismograms, that basically just through a series of complicated levers attach that pen directly to the mass. So this guy from Italy, Filippo Cecchi, in 1875, came up with the first sort of machine that did this successfully. So you can see here, it's really kind of like the cartoons. He has a big ball that's suspended by some springs, and so that's going to stay in the same place. Everything else you see here is going to move in the earthquake. And when the ball moves, it's going to pull on these levers that are going to move those pens and scratch a record onto the drum. So there's the mass. Those are the drums. And this turns out to be one of the earliest recordings we have of an earthquake in what we would consider to be our modern sense. So this was an earthquake that happened in 1887. This was a station near Torino in Italy. And the earthquake itself was on the Côte d'Azur in France. So it was actually measuring something pretty far away. It's about 140 kilometers away. And he was able to measure and say that, well, it was not doing much, and then suddenly the ground starts to shake. So this was really the first success of measuring an earthquake, but as you may or may not know, we can actually measure earthquakes from really, really far away as well. So in earthquake terms, measuring something that's 100 miles away is actually pretty easy. That's pretty close. We also have something called teleseisms, and the first one was recorded in 1889 by this guy, Ernst von Rüber-Paschwitz. I don't know if I pronounced that right. Someone helped me with my Italian, but I didn't have anyone to help me with my German. He was in Prussia in the late 1800s, and it comes sometimes from odd places. He was actually trying to measure gravitational changes on Earth due to other planetary bodies coming in close orbit. Mars or Jupiter or something like that. So he had a very, very sensitive instrument and a big mass, essentially, to try and measure gravity, right? The mass would become more attracted even to Jupiter coming close, and he would be able to see the motion. And he just had this thing running because he wanted to see if he could track celestial bodies. And what he found instead was this. So this is recorded in 1887 in Potsdam, and he said, well, what is that? It's not like a planetary body came screaming in, changed the gravity, and went screaming away. And it turns out he had effectively, without realizing it, built a seismometer. And this was an earthquake in Japan. So he managed more than 100 years ago, closer to, what is that, like 130, 140 years ago, to measure something almost the entire opposite side of the Earth that no one would have felt, right? When there are big earthquakes in Japan or in Indonesia, we don't feel them here. The only way we know it happened is there might be a tsunami warning, which is a separate matter. That's a whole other talk. But in this case, there was no reason other than this guy trying to measure planetary bodies that anyone in Germany should have known about that earthquake anytime in the next few weeks until the news reached them. So the point I want to get across here, and sort of the thing that amazes me, beyond even what we can measure in volcano science, is that we can measure stuff this precise at all. Seismometry is a science. In other words, the measurement of things that are moving actually spans a massive order of magnitude. I don't know if anyone here knows about NIST, the National Institute of Standards and something, but they're basically the people that tell us exactly how much a pound is, or how much a foot is, or, if you do the SI system like the Europeans, tells us how much a meter is, or how much a kilo is. They don't regulate seismic ground motion because they can't get precise enough to create a standard. We can measure things for over 8 orders of magnitude. So period is just how long it takes for a wave to go through one cycle. If you go out surfing or go down to the ocean, you'll often hear about swell having like a 20-second period because you're counting 20 seconds between the peak of one wave and the peak of the next one. So those are waves, just like the sound waves and the seismic waves. In seismology, we're able to measure seismic waves that have a period of 100,000 seconds and seismic waves that have a period of 1/1000th of a second. So that's 8 orders of magnitude. Period is kind of hard to understand this idea of big orders of magnitude with. So in amplitude, it turns out we also can measure really, really massive differences, even if they're quite small. So what this plot is showing you is essentially how much shaking, the strength of shaking we'd expect from different kinds of earthquakes and different kinds of waves. So up here, we essentially have the biggest waves from the biggest earthquakes. These are your magnitude 9 in Japan sort of earthquakes. And down here, we have sort of the magnitude -1, 0, 1 earthquakes, the ones that don't even wake us up at night and we're right on top of them. The reason we know they exist is seismology can measure all of them, oftentimes even with the same instrument. So we can measure a -1 magnitude earthquake, which is equivalent to taking a ruler that can measure the diameter of an atom, a single atom. And then we can take that same ruler, that same instrument that we use in seismology, and we can measure those bigger waves, those enormous waves that are equivalent to the height of the room. Now, the waves themselves are not the height of the room. That would be problematic for a lot of us. But the point is, imagine using a single tool to measure something that's as small as an atom and as big as this room. That's really pretty special, I think. Now that you've listened to me be a nerd for about 20 minutes, I can tell you about why it's actually really important that we can do this, that we are able to harness this physics and be able to measure how the Earth moves. And what we'll start with is, well, earthquakes, what we typically think about. In the typical earthquake cycle, what we do is tectonic plates are sliding by one another. They're going to build up stress with time. For example, here we have this nice rock wall. Everything's hunky-dory. And as the stress builds up, we see that the ground and the rock wall that's on it is starting to bend. Now, eventually, at a certain point, an earthquake happens because we can't bend anymore, and it breaks. And then we'll snap back, and you'll see that the wall is now offset. The ground itself has moved. This is sort of the classic earthquake, if you will, the regular flavor. And this is what we see all around the world when we talk about the ring of fire and the fact that we worry about earthquakes in California, in Washington, in Alaska, in Japan, down through Indonesia, through Fiji, across South America's west coast. That's because those are all the boundaries of tectonic plates. There is one, or more than one, there's one particular spot that I put in the middle of the map because it's important. Right here, though. There's no tectonic plate there. And there are all these earthquakes in the middle of the ocean. And that's us, here in Hawaii. So we have not quite the regular flavor. We have a little different kind of earthquake here, and we have actually several different types within that. So we can get some earthquakes that are volcanic, but we can also get some that are not. So I'm going to talk about the boring non-volcano ones first. We can have earthquakes that are on what's called the décollement. That's just a fancy way of saying that's where the island, all the lavas that came out of the volcano, are sitting on top of the oceanic crust. Now, if you have a big trampoline and you start dumping gravel onto it and making a big pile, eventually that pile is going to want to spread out. You can only stack it so high. It's very much the same when we start building up our volcanic island. Eventually, we stack it up too high, and it needs to spread out. These are actually really scary earthquakes. The earthquake down in Kīlauea that was over magnitude 8 in the 1880s, the 1975 one. These are examples of what can happen when that whole edifice slips and the island spreads out a little bit. Now, there's another star here, so you can probably guess I'm going to talk about something that's down here instead. And you can also have earthquakes that result from flexion. So as we're loading up that trampoline, because the trampoline is bending, because the plate is bending, you're going to have compressive forces up at the top and extensional forces below. Right? If you want to take this sheet of paper and I tried to bend it, I'm stretching the bottom and I'm squeezing the top. So when we do that to the plate, when you have stretching or squeezing, you can generate an earthquake. And if people remember the 2006 Kīlauea Bay earthquake, that was one of these. The last type of earthquake we have in Hawaii, and the one that is probably most interesting to folks here tonight, are the volcanic ones. So it turns out, aside from the island itself moving as it settles and it gets built up, there's a lot of movement that happens because we have magma coursing through the island underground, moving different places, and sometimes erupting. And what seismology allows us to do, here's kind of a nice schematic someone has made, a cartoon, if you will, of where earthquakes are. It allows us to actually really look down into the plumbing of the volcano that we otherwise don't really get to see from the surface. And what it does is allow us to differentiate when magma is actually moving or creating new pathways, or where it is essentially underground. It's a nice view into that. So there are a couple different ways magma can move. One is that it can crack open the earth, right? Deep underground, if there's a solid rock and magma needs to get through it, it will often crack that rock. And as it opens those cracks, it can come in and occupy it. This is essentially brittle failure, just like this poor log being split apart by this axe. The magma is pressurized enough that it's moving in there and splitting apart the rocks, causing the rock to fail. I like this picture. There's a pool there, and it looks like someone either has jumped in as a giant cannonball or something. It's sloshing around a lot. If you actually look out at the edge, this is on a cruise ship. This is a pool on a boat in the ocean. And so as the boat rocks back and forth, the water is sloshing around. In the volcano, we might have these big magma chambers. And as we change the pressure going into them, that's going to similarly slosh the magma around. And that, just like you'd probably notice if there was a big pool of water sloshing around, creates a seismic signal. And kind of similar to that, not necessarily just sitting in a big pool, you could have water shooting through a pipe or a hose. If you run your garden hose at home and you turn it all the way up and you're holding onto it, you probably feel a slight vibration as the water is flowing through. Same thing if you have a conduit, if you have a tube or a pathway through the rocks where the magma is flowing. As it flows through, it's going to create vibrations that are going to be picked up on our very sensitive seismometers. Now, with all these different ways that we could create a volcanic earthquake, we have given them some names. This is a volcano-tectonic earthquake, or a type A, because we're very creative when we name things. This is the brittle failure method. And just like you might kind of expect, it happens pretty suddenly. Bang! You just break the rock, and so there's a sudden movement, and then the energy sort of just decays away after that. So this is the brittle failure, where we get a big pressure change, maybe from a magmatic intrusion, magma moving through the earth into someplace new, or maybe even magma moving away and no longer supporting some rock above it. And what you're going to notice is that these have a shorter period, they happen pretty quick, and they have a high frequency onset, so they start pretty quickly. Without going into too much detail, this is a visualization of how much energy there is as a function of time. And so what we're looking at here is that it really kind of dies off pretty quickly. The other type of earthquake, this is type A. You might be able to guess the next type is type B. Type A, type 2, part C, right? So the long period earthquake is the second one. This is type B. And it's so named because it has longer period. That's because it's from these resonant oscillations. So these are the earthquakes that happen as a result of that sloshing of magma in the volcanic systems. Like we said, you can kind of get this sort of earthquake if you change the pressure. That could be from unsteady flow rate, or any case really where you're kind of changing the speed, if you will, of things going through, like a small conduit. That's going to change the pressure, and as a result, slowly move the ground and oscillate it back and forth. And because this is sort of a slower process, you don't really want that to happen all of a sudden, it has what we would call emergent first arrivals. So if you remember that VT earthquake we saw, it kind of went up and down really quickly up here and then decayed away. That is not what's happening here. In this case, the shaking slowly kind of emerges. It starts, it increases, and then it slowly kind of dies down. They're smaller than volcano-tectonic earthquakes, those type A VTs, and they have more energy at low frequency because simply they're sort of just moving along slowly. I didn't do that. I don't know why the lights did that. And all the energy is more or less down here. Now, that kind of sloshing can just go on for a while, right? You could imagine, like in the hose, where the water is just flowing. It just keeps on moving along. And in that case, it could last not only longer than VTs, but just keep on going almost constantly. This is what we'd call volcanic tremor. So this is our hose case. The lava's just moving, the magma, I guess. It's underground. The magma is just moving through the volcano, and it's slowly just shaking everything as it goes along. You can kind of think of these as resonant oscillations. Again, that's what they are, but they're long. They go on for minutes, hours, maybe even days. And as a result, it's the exact same sort of things, resonant vibrations, maybe degassing. You'll see that the energy just kind of sustains, right? This is almost an entire minute in this case, where it just keeps on going. And if we kind of look at all of them next to each other, you can see there are very different time scales. So here's our VT, shaking starts pretty suddenly and dies away. Our LP, or low frequency, long period, it starts up slower, and you can actually tell it's not going back and forth as quickly, up and down as quickly. Then we have the tremor. That's when we take one of these and we just make it long. Do it for a while. And then there are two more that are also not very creatively named. If you have an earthquake that has a lower frequency than a low frequency earthquake, well, that's a very low frequency earthquake. The shaking is even more drawn out. And if you have an earthquake that combines the rapid, quick up and down onset of the volcano tectonic and the slower, longer lasting low frequency earthquake, long period, then you get a hybrid. It's the two put together. So with these earthquakes, you can actually kind of now start to interpret what might be going on a volcano, right? If you see these guys, you're breaking things. The magma might be moving into a new area and creating a new pathway. If you see these guys, the magma's kind of starting to move, it's sloshing, there's some pressure changes. And if you see this, it's really moving. It's moving enough and in high enough quantity or close enough to you that really that's all you see. It just keeps shaking. So how does that sort of key in when we actually look at seismograms? Let's just revisit so we remind ourselves. Here's our seismogram. It's going to shake everything except the mass, and we're going to get a drawing, essentially, of the shaking. There's a small wave, there's a bigger wave, and as a result, when we unwrap it, we get a seismogram. This one's pretty boring because there's no volcano earthquakes on it. It is actually here for a reason, though. There is sort of a side story that I'm happy to talk anyone's ear off about if they want, which is that, I see Liz making a face down here. If you look at the date, this is July 1945. So you might see some shaking. This here is not an earthquake caused by tectonic plates, even though it's down in the American Southwest. That's the first nuclear bomb we detonated. So all kinds of things show up on seismograms. It's not just regular earthquakes. It can be our volcano earthquakes. It can be magma moving. It can be the rain falling really hard on my house. I see that. I have a home seismometer because I'm a super nerd. Okay, so back to the volcanoes. When we look at a seismometer, you can probably see in this case we have two very different looking earthquakes because one is a VT and the other is an LP. I shouldn't have said one because one's not actually the VT. Number one is an LP and number two is a short period. In other words, this one you can really see when they're side by side, starts really quickly and decays very quickly after. And this one starts more slowly and lasts for a much longer time. And the reason you'd want to be able to tell them apart on a record is that's really sort of how you start telling the story of what's going on when you look at a volcanic seismogram. So here is a set of records, or one record, from Makaupuhi crater, 8 February 1993. It's a little older because that's when they were still using those drums, and I like the old records. We see a lot of these VT earthquakes, right? All of these have this, essentially this triangular shape. They start shaking really quickly and decay fast. And what that tells us is that in this area, those of us that need the reminder, Here's the national park, chain of craters road coming down. This station is over here, kind of getting about halfway down chain of craters road, about where the East Rift Zone is going to start shooting off down towards Puna. And what's happening then, in this case, is that, okay, we're probably breaking through some rock and creating a new intrusion in here. It might not lead to an eruption, but it's good to know that something is probably new and moving through this area and creating all of these volcano-tectonic earthquakes. And now the key is that we can actually use the fact that there are a bunch of stations, not just this one further down the rift, to really get the story of what's going on at the volcano. So sure, we established all these VT earthquakes means we're breaking stuff down here. We're creating a new pathway. What about this one? This is the same day, 8 February 1993, but this is a different station. This one is the North Pit station, which is up at the crater at the summit. And in this case, these are not VT earthquakes. In fact, they're barely earthquakes at all. You'd call this tremor. It's just constantly shaking as there's magma moving. And where there are kind of earthquakes you could tell, we'd probably call those LPs. They're pretty drawn out. They don't have that triangular sort of shape like the VTs. And the interpretation in this case is that, well, all that magma, which is breaking the ground out near Chain of Craters Road, needs to come from somewhere. And now over here, further up in the system, we're seeing the plumbing with a lot of magma flowing through it as it's feeding that intrusion into the East Rift. Here's another one. This one has both at the same time. So rather than looking at one place where we have magma flowing rapidly and one place where it's breaking through the rock, this is the same station. This is North Pit again. We have all these VTs and then some LPs, so it's breaking through the rock, and then it's starting to flow, and then it's really flowing, right? And when I say flowing, that's not like over the surface. It's nowhere near the surface yet, or not visible at least. It's just underground. It's starting to move. This is a record, again, from North Pit in 2008. This is right before that large set of explosions, if people remember that. There was a bunch of degassing. They closed down the west side of Crater Rim Drive. They threw some big rocks out of the big hole in the crater. And then eventually we got a lava lake. To get that lava lake, we had to have magma up near the surface. And before any of this happens, we have the seismic record of both the breaking of rock and then the magma actually coming in and filling up spaces. So this is still true now. I do want to, I'm talking about stuff that was over 20 years ago. We can do this now, and because it's so nice of a way to look at seismic data, even for the digital instruments, you'll notice if we just go to the Google machine and type in Hawaiian Volcano Observatory, you too can look at seismometers from home. So let's just click Hawaiian Volcano Observatory, and we'll get a nice map. Here's the crater. And let's just look at Keanakakoi. If you find these black triangles, don't ask me why. For some reason, seismologists the world over for decades and decades have decided we're going to denote a station with a black triangle. No one does it any other way. Don't know why. But if we look at KKO, what you're going to see is a whole bunch of seismographs. Just like the ones we looked at, you're going to read them like a book. Left to right, top to bottom. Let's look at the past 2 days. In this one, we can see this is after that last big episode 40 ended. We had a couple of swarms. And in this case now, you should be able to tell those swarms are actually volcano-tectonic earthquakes. They have those triangle shapes. And so because they're VT earthquakes, we know that something's probably going on and breaking through rock, maybe creating some new pathways. The rest of these are LPs, where the magma is resonating and the fluid is probably sloshing back and forth. And we have a little bit of tremor in here too, where maybe it was actually filling a little more rapidly. So in some ways, for me as a seismologist, the most exciting part of this current sort of eruption is when it's not fountaining, because that's when I see stuff refilling underneath. We see all the stuff that we can't see at the surface. So this is the exciting part for us. And the nice thing is, I am what I like to think of as a historical seismologist. And what that means is we try to use all of the data we have. All the things I'm showing you so far, except for what we just looked at, is from this era of analog recording. We talked a lot about paper on drums. And that's actually what we used to record this well into the 1980s. Jagger showed up in Hawaii in, I think, 1916 or something like that, and brought seismometers with him. So we've been recording earthquakes here and volcanic activity for over 100 years, but most of what we have is covered by this bar here, the analog recorder. It covers a lot of other interesting stuff too, and there's a reason that we should care about old paper seismograms. If we look at all the large earthquakes that have happened since 1900, we're actually missing some. These are everything over 8. So here's that big one in Japan, the 2011 Tohoku one. Here's the 2004 Indonesia earthquake that created the Indian Ocean tsunami. Those aren't the biggest ever, though. Alaska in 1964 and Chile in 1960 are. We haven't recorded anything bigger than those two, and they're only recorded on old paper records. I did show that Trinity test for a reason. It turns out that when we want to study what nuclear detonations look like, including what they look like when Russia or North Korea is doing them, we need to look at old seismic records. It's a good thing that we stopped doing it, but for a while at the end of the 20th century and the second half of the 20th century, we were detonating a whole ton of nuclear bombs as tests. We have recordings of all of those, and they're sitting on historical records. And then, of course, here, we have the volcano. All of these figures here are on this time scale. So this ends before all of the newer stuff, 2018, and now the ongoing activity at the summit. But you can see that there was a lot of sort of Pu'uo'o activity, Mauna Loa being inactive, that covers the digital span of recording here in Hawaii. And otherwise, if we want to look at all these other black lines which are eruptions, right? All the Mauna Ulu eruptions that happened in 69 and into the 70s. Or the last time we had summit activity coupled with rift activity, which would be 1959, Kīlauea Iki, 1960, down in Kapoho. That's all covered in the old historical records. So one of the things that I work on, and if people want to hear more about that or wonder how they too can go scan seismograms, is historical seismology, which is taking this historical data and looking for this really important, invaluable information that can contribute to long-term understanding. Being able to unlock the data in here is something that could increase our ability to understand the volcano many-fold. The downside to doing this is retrieving data from historical instruments can be challenging. This is the basement of the Hawaiian Volcano Observatory up in the park, when it was still up in the park. All those boxes contain several months' worth of seismic records, probably hundreds of records in each of those boxes. And as you can see, there are thousands of boxes going down across the basement. And it's challenging to get through them. It was challenging to get through them when it was all up in the park. After 2018, these got moved. Some are still here. Some got put in long-term storage in Denver. So we need to be able to get at those records and make the case that we can use them still. And the reason we should do that, even though it might mean going to Denver to get records now, is that we can expand this time window and we can look at events like Mauna Ulu and Kīlauea Iki and the last Kapoho eruption to really do a better job of trying to understand long-term behavior on the volcano. So overall, essentially what I'm trying to advocate for is just looking at the volcano, not just in more detail or with more stations, so that would be great, but also over a greater time window. We have a whole treasure trove of old records we're sitting on, and there's a lot of richness that we can pull apart. Speaking of pulling things apart, I do actually have, now that I'm more or less done here, I have some old seismograms that are of interest perhaps to those of you that might want to look, and some taken apart seismometers. So I'll take any questions. People can come down and look at some of this stuff. I'm trying to get rid of tangerines from my grandpa's tree, which is going crazy. So another reason to come down, even if you might have to talk to me. And one more time, just to give people the run by, there are more things happening. So there's a guided walk on the 16th. There's an eruption update talk on the 17th. Another guided walk in the park on the 19th. And then a talk story on the 20th. Megan down here is doing that guided walk, and it'll be great. And then I'm going to pick on Liz too. Liz is going to be up at the volcano doing Volcanology 101, which will be more detail on sort of the larger scale. Well, what is a volcano? What is it doing? How do we know what it does? Up on the 29th? Sure. I'm going with the 29th. I'm locking in my answer. And so, yeah, with that, I'll take any questions, and I'll chat with anyone who wants to chat. Thanks very much. Put on more lights. Oh, you know, I have a PhD, but not in light switches, apparently.
I think the room is,
Question.
Your description of the seismograph machine
Sure.
is a one-axis machine, but shaking can occur in three. So what do you do about that?
Absolutely. It's actually a pretty simple answer. Oh, sorry. So the question is that the seismometer I was talking about is a one-axis machine. In other words, we're only measuring how much the ground is moving in one direction, right? If we look at, where'd it go? If we look at this guy, we'll bring back Newton. This ruler and the ball are only moving up and down, so we're only measuring vertical motion in this case. If you want to measure the other two directions, two horizontals, east-west and north-south, you just simply need two more instruments. And in those cases, you have, instead of a vertical instrument, you have a horizontal one. So usually it's a pendulum sitting out on a ledge.
I understand that, but you've chosen to measure only in one direction. That's because typically most of the motion is vertical?
We actually measure all three typically. For simplicity here, I talk mostly about the vertical. But generally, and this is part of the problem with historical seismic records, we have a ton because one station didn't mean one record every day. It meant 6 because we had 3 directions of recording and we had 2 sets of instruments, one for long period and one for short period. We actually had, at that point, the ability to record only a certain bandwidth because if you can imagine that thing about the size of an atom or the size of a room, the instrument could detect that. But you'd need a massive sheet of paper to be able to see things that are the size of an atom and the size of the room. So the limitation was really the size of the paper. So we ran 2 sets of instruments, tuned differently in 3 different directions. So 6 different recordings from every single station every day for decades and decades and decades. So that's why we have millions of old seismograms to get the complete motion.
The second part of that is when you're talking about measuring the distance, the diameter of an atom, a truck going by will do that for you very nicely, I'm sure. So how do you isolate or discern the difference between human noise or man-made noise and real seismic noise that's lower in the scale?
That's a great question. So the question was, how do you measure the difference or tell the difference between man-made sort of seismic noise and the sort of earthquake type things? One answer is that, if you can locate an earthquake, which is generally done with triangulation, by figuring out when different waves arrive, you can get a distance to an earthquake or to any source, whether that be a truck or an earthquake, from a station. And if you have more than 3 stations, you can do the triangulation exercise and figure out not only where it is in latitude and longitude, but also in depth. It's actually pretty rare to get earthquakes that are right at the surface. Most of them are at depth. So once you have a location that's going to be 10, 15, 20, 40 even is a pretty typical depth, kilometers under the ground, you're generally quite sure it's an earthquake. The other reason is that seismic noise if it's anthropogenic, man-made that is, generally has, if I can find my mouse here for you, a pretty different signature. So one thing that I'm also going to show off here is raspberry shake, which if you want your own seismometer, you can buy one for about $1,000. That's what I have in my house. And it allows you to see the shaking. So it's an open network. You can go online and Google raspberry shake and see the same thing. R9F1C, I think, is the instrument that we have that sits behind Steve's office in our building. And if we look at that, come on, there it is. If we look at that, we wouldn't interpret this as a lot of tremor and then the volcano kind of took a break and then a lot more tremor. This is just the typical cycle of the air conditioning in our building. So if we actually go and zoom that out or see it a little better, there's actually a whole richness to this as well. You can see exactly what time the AC kicks on in our building, right about 5 a.m. Hawaii time. It runs through until it dies down. It looks like it kicked off somewhere up there, probably about 11. And then in between, you can actually see there's a dehumidifier that switches on and off on some timer. So, yeah.
Thomas, you had mentioned too the nuclear testing that shows up on the seismometers, which makes perfect sense. And two-part question. One is, I'm certain our intelligence industry back then was probably really interested in these data, but from most of what you've said in this talk and others, that they've been sort of left alone and not really touched. I mean, has USGS been rated for nuclear information by people with other interests? I'll ask that question first. Yeah.
So the question was basically about what happened to all the seismograms with the nukes on them, essentially. Those are still out there. The defense industry and the US government did actually fund what was called the Worldwide Standardized Seismic Network in the 1960s. And it was exactly that. It was the first standardized seismic network with global scope. And it was put in place for verification of the Comprehensive Test Ban Treaty, which was being negotiated at that point, because no one wanted to come to the negotiating table unless there was going to be a way to say that, no, you guys didn't detonate anything over 60 megatons in this period, and so on and so forth. So they needed a way to actually check their results, so to speak. So that's when that went in. And those records still exist. The problem is that they need to be digitized. They are on paper, and someone needs to go in and trace through the records. So a lot of my doctoral work was actually trying to figure out how to do those sorts of things. So there's a small handful of people that are trying to do it, and that's where a lot of those records are.
Second part, is there any difference in those near-surface detonations in terms of the kind of data that geologists would want to use to understand aspects of the mantle and the lithosphere that don't come from the typical kind of earthquake? Is there something different that you can learn?
Not particularly, since at the surface, a lot of times when people do try and do seismic prospecting, you can do it with a lot less of a violent sort of source than a nuclear bomb. There have been experiments, including one up at the park, that took what was called a thumper truck. So it's just a utility truck with a little pneumatic ram on the bottom, and it thumps the ground in a known way, and we put out our seismometers and we look for the signals that come out. So that's the near surface bit. As far as having a deep bit, we've only dug 12 kilometers down into the crust, so the earthquakes that are 600 kilometers down are more exotic and give us a lot more sort of information than sort of the nuclear type of detonation can. Yeah?
Thank you for a nice talk. I was wondering if you could go back to a slide that has the deeper drum seismograph.
Yeah, I sure can. If I can find my mouse. There it is. How's this one? Oh, that one.
Not that one. That's a bad one.
This one?
No one that's like showing, like the full slide was like the paper of the drum. Yeah, this one's okay. So like there's this periodic signal that happens like some set time interval. What is this?
These guys?
Yes.
They're time marks. They happen at a set time interval because they're for telling the time. So every minute, after every minute had passed, there was a clock that told the entire drum that this paper was on shift by a little bit for just a second. And that gives us these little offset portions. So when we say left to right, top to bottom, it's too small to see, but these little longer tick marks, if you can make them out, those measure every hour passing. So if you wanted, I can't actually read the notes, but let's just pretend this is like 2000. If this is 2000, then as we go across, 2000 in 1 minute, 2000 in 2 minutes, 2000 in 3 minutes, and so on and so forth. So it's simply a timing mechanism. Yeah?
When they use these papers, when they change the paper, there were no measurements?
Yep, so there's always, you know, if you're really fast, there might be less than a minute of dead space on the record. But otherwise, yeah, it is not recording for as long as it takes to stop the instrument, unwrap the paper, wrap a new one, and start it up again. But to the other question about having, you know, different directions of recording, and in fact 6 different instruments, you didn't do all 6 at the same time. So in the old days with those stations, it was still a pretty continuous set of records because at any given time there were 5 instruments recording, guaranteed. Mostly there were 6. Yeah?
So you discussed how the old analog seismograms work, but how do the new digital ones work?
So they work very much the same way in that there's a mass which is suspended. Here it is. This mass is right here. And you can see it can move up and down, and there's some springs that would usually hold it up in here. That actually works almost the exact same way as the old seismometers. In fact, what we have done is just take an old seismometer and hook it up to a computer, because the way it actually measures stuff is not with a ruler. You might be able to see there's all this red wire wrapping around. It's a magnet in a coil of wire. And so when it moves, we know that we induce an electrical charge, we induce a voltage in that coil of wire. So really what a seismometer is doing is it's moving a magnet up and down in some wire and inducing voltage that's proportional to the movement. On the old records, you converted that voltage into the swinging of a pen armature, and that's where you ran into dynamic range problems. So really, all you do to get a modern-day seismometer instead is just hook up a voltmeter that can record the voltage to it. And that gives you that big dynamic range. Yeah?
All right, thank you, Thomas. And if there are more questions, you can test them in person.
Yeah, come chat. Please come take tangerines.
All right.
Gentlemen.
Yeah, I think he does an amazing job at presenting. That was the first time I've heard him speak, and explain some complex stuff pretty simply.
Yeah, I think we said similar to a start there. Yeah, yeah, it was pretty good. Intro level seismology talk, like lots of things that people, a lot of our audience might be watching on the seismographs or signals coming in, things that you can learn that maybe we take for granted sometimes. So yeah, really great review of all that stuff.
I think it was good timing considering we're having all the earthquake activity. I mean, yeah, perfect. Any other time in the year, in this last year, we haven't had this heavy of earthquake activity, so it was perfect. Yeah, definitely.
Yeah, so appreciate the USGS Volcano Awareness Month and UHilo and Professor Lee for that. That was a great little recap. And although we're at the very end of a long update here, and just thought I should show you guys a couple of things. One is just a current live stream here where you can see there was actually some spattering happening from time to time during there on the live stream. And also we have had the USGS in that time where we were showing in the presentation, release an information statement, which is just shown here for you guys. And this is just, as I say, a review of recent observations and summary of what could be expected next. Issued at 6:20 p.m. today. And besides reviewing all the recent information, possible outcomes stated in bullet point, eruption continues, new vents in the summit or upper southwest rift. This is interesting. A new tie together. They note that because of the activity in the southwest rift in 2024, made numerous new cracks, many covered with tephra from the recent fountains. that could be an area that there could be transition from summit to upper southwest rift zone activity, similar to 1919 in Mauna Iki. Or third option, and separated to be noted as the least likely, an east rift zone intrusion or eruption. So there's still a lot that a lot of hurdles you'd have to cross before having an actual impact to people in the lower east rift, for example.
Right.
So that's basically it. Anything you guys want to add here?
No, I think we covered quite a bit tonight. It was all kind of came together with the earthquakes, the talk, and activity picking up in the caldera.
Right. And we'll be back next week, Thursday, 5 p.m. or Hawaii Standard Time or normal time, probably covering episode 21. But before that, we will be in Ocean View on the 24th this Saturday.
I lost this. Hold on, gentlemen. Sorry, I clicked a button. You had it. It was good. There we go. Sorry. I was trying to maximize our event for this weekend.
All right. Can we get it going?
Good.
There we go. So yeah, event happening this Saturday, 2 p.m. Hawaii Standard Time. We'll be live streaming that one and hopefully have a bunch of presenters and some good questions, stuff like that. If you do have a question for civil defense or USGS, Lou dropped a link for a form. You can go ahead and submit your question there, and we can try and get it asked. And that's we'll probably be covering episode 41 here on Thursday, and then next week we'll be bringing, or the week after that, be bringing you Liz Gallant's speech, I believe. So that's the rundown. Looking forward.
All right, sounds good, gentlemen. Thank you. Since we're so far in, I'll just sign us off unless you got anything else to say.
Let's roll.
So
good.
Yeah. So until Saturday, 2 days from now, and then following next week, Thursday, from our nonprofit HVERI, the Hawaiian Volcano Education and Resilience Institute, we have Lou Hattori, Dane DuPont. I'm geologist Philip Ong. Aloha, everyone.